Welcome to EDU World Space.
Today we're going to talk about the photoelectric effect. So the photoelectric effect, happens when we have the emission of electrons, those red particles, due to photons. So remember first that the characteristic energy of photons is proportional to Planck's constant. So I'm right here is Planck's constant times the speed of the light divided by the wavelength of the light beam. Okay? And when the light beam hits the electrons that are bound to a material, what is going to happen is that if the energy of the photon is larger than the energy of the atomic binding between the electrons and the nucleus, then the electrons are going to be emitted. And we're going to have the following expression. We're going to have that the binding energy of the electrons in the material, that we call the work function, plus the kinetic energy of the electrons after they leave the material, so Kmax, is going to be equal to the energy of the photon. Okay? So part of the energy, when the energy of the photon is greater than the work function, part of the energy goes to release the photon from the atomic binding, and the remaining part, if any, goes to the kinetic energy of the electron. Okay? And people actually measure the kinetic energy of the electron by trying to stop these electrons with an external electric field. So they measure the kinetic energy to be equal to the energy of an external electric field. Only HV0 is the so-called stopping voltage. Okay? Now, in this exercise, we have a photoelectric experiment on which we have on which we know that the minimum energy that the photons must have in order to release the electrons from the atomic binding have to be such that the wavelength has to be at least has to be smaller or equal. So let me put this here. Has to be smaller or equal than, in order to have photoelectric effect, 550 nanometers. Okay? Now, knowing this, the exercise wants us to calculate what is the work function for the electrons in this material. Okay? So, the work function, remember, is the minimum energy that the photons must have in order to release the electrons. So given this, we have that the work function is going to be the minimum value that lambda can have in order to observe the photoelectric effect. So lambda 0 divided, C divided by lambda 0. C divided by lambda 0, on which we know that lambda 0 has to be equal to 550 nanometers. So let's just substitute the value. So Planck's constant in electron volts is 4.136 times 10 to the minus 15. The speed of the light is it's 3 times 10 to the 8 meters per second divided by 550 nanometers, on which nano is 10 to the minus 9. Okay? Do this calculation, we're going to find that the work function for the electron is going to be 2.25 electron volts. So this is the answer for question A. Now, in question B, the exercise wants us to suppose that we emit a light beam with a wavelength of 400 nanometers. Okay, and asks us to calculate what has to be the stopping voltage for this case. Okay, now if we go back to these two expressions here, okay, we can use, we can see that we want to find the stopping voltage. So we want to use this expression that I'm going to call expression 2, and we're going to use the expression for the photoelectric effect, okay? So let's substitute 2 into expression 1. So we're going to have that the work function plus the charge of the electron times the stopping voltage has to be equal to the kinetic energy of the electron. Has to be equal to the energy of the photon. Okay, now we can isolate V0, and we're going to have that V0 has to be equal to the energy of the photon times, minus the work function divided by the charge of the electron. Now, we can rewrite both EP and W in terms of the energy, in terms of the characteristic and expression for the energy of the photon. So we have that V0 is going to be Planck's constant times C divided by E times 1 over lambda minus 1 over lambda 0. Okay, now we just substitute the values. We have that V0 is going to be Planck's constant 4.136 times 10 to the minus 15 electron volts times the speed of the light, 10 to the 8, divided by the electron's charge, which is 1 electron. I'm not writing in coulomb, okay? I'm writing in electron, so I can divide electron volts times second by 1 electron. So we have volts times second in here, times 1 over, so the wavelength, 400 nanometers, so 400 times 10 to the minus 9, minus the maximum wavelength, which is 550 times 10 to the minus 9. And with this, you're going to find that the stopping voltage has to be 0.84 volts.